morning, everyone. My name is Diane. I'm the Communications and Events Center. And it's my great pleasure this morning to invite, or to introduce rather, Prof. Vishnu Jejjala, who is joining us from the US. So thank you very much, Prof, for joining us so early this morning. He is a professor in the School of Physics at Wits University, but currently on sabbatical in the US. I hope I got that right.
Yeah, that's right.
And today he's going to be presenting with us on the topic of deep learning topology. So, Prof, I will hand over to you, and thank you again so much for presenting with us.
Okay, so I hope everyone can see my screen. The work I'll describe is some stuff I've been thinking about for a few years now on applying machine learning to areas of mathematics that have interest to theoretical physicists. So in particular, I'll tell you about some aspects of topology of knots to begin with, which are related to certain quantum field theories that are natural to think about from a physical context, and then about so-called Calabi-Yau manifolds, which I'll tell you about, which are useful for compactifying string theory down from 10 dimensions to 4 dimensions and recovering aspects of particle physics and cosmology in the real world. So please do interrupt me for questions. I'll try to start from a very elementary level and take it from there. Okay, so let's get started. So topology is really about the shapes of objects. And the shapes are sort of independent of certain small deformations you can do. In particular, two objects are considered to be topologically equivalent if they can be continuously deformed into one another. For example, by bending or twisting or stretching or crumpling, but not by things like tearing or cutting or gluing. So you're allowed certain operations that are somewhat tame and disallowed other operations that are more severe. So formally, there exists a homomorphism between two spaces. And we more or less have an intuitive notion of what topology means. So for example, you'd never mistake a soccer ball for a donut. They've got a different number of holes in them. So they're topologically distinct objects. But at the same time, the donut also has the same number of holes as a coffee mug. So these things would be considered topologically equivalent, even though they look nothing alike. So topology was one of these areas of mathematics that is very classical, and the ancient Greeks were thinking about topology in some sense already. So famously, there are 5 Platonic solids, and Theaetetus was the mathematician credited with discovering the dodecahedron and the octahedron to complete this list. They're called Platonic solids because Theaetetus happened to be a friend of Plato and was a subject of a famous dialogue which established the philosophical field of epistemology. The Platonic solids have a property which we remember from our primary school. If you count the number of vertices, the number of edges, the number of faces, and you take a combination of these, v minus e plus f, you always get the number 2. This was realized by various people. Moralica was maybe the first person to realize this in 1537. Euler rediscovered this in 1752. It's called the Euler character, or Euler characteristic now. Moralica, incidentally, was the man who invented the proof by induction. So he's got some place in mathematics just for that innovation. So we have this Euler characteristic. The Euler characteristic is what's called topological invariant. So all of these different shapes, they have the property that v minus e plus f equals 2. And the reason that v minus e plus f equals 2 is because these are related to things you can draw on a sphere. So all of these Platonic solids can be projected onto the sphere, and the sphere is an object with Euler character 2 as well. In fact, the definition of Euler character for these objects with holes in them is given by the genus. Genus is basically the number of holes, and 2 minus twice the number of holes is the Euler character. So the sphere has got no holes in it. So 2 minus 2 times 0 is 2. And in physics, we often think about a spherical cow approximation in doing various problems, teaching our undergraduates. And for our purposes, the cow is a genus 0 object, and the coffee mug and the donut are genus 1 objects. They both have one hole in them. So a topologist morning consists of a cup of coffee, putting on his trousers, and putting on the shirt. These are objects of genus 0, genus 1, genus 2, and genus 3. In physics, we encounter topology in various contexts. So the first place undergraduates may see and appreciate topology is in looking at Gauss's law. Gauss's law tells us about the flux through uh, some um, some shape containing charges inside. So we often draw pictures of spheres when we do this. We think about a charge, we think about a sphere that contains this charge. We think about electric fields lines that are passing through the sphere. But there's no reason we should draw a sphere. We could draw any shape whatsoever, and we get the same Gauss law out of this. So this is an example of topology making an appearance in physics. The behavior of this mathematical quantity, which is obtained in Maxwell's equations of electrodynamics, is independent of the actual shape of the object that surrounds the charges we're considering. Similarly, another of Maxwell's equations, Ampere's law, is based on looking at a shape that goes around a current which is traveling through a wire. The shape we draw can be anything at all. It just needs to enclose the wire, and the magnetic fields associated to this current are computed independent of this shape. In quantum mechanics, famously, this is a Aharonov-Bohm effect, in that when we consider the wave function for a particle that's charged, is moving in some region of space, and suppose there's a solenoid which contains a field which passes through the solenoid. The particle, because of the solenoid, never actually experiences a magnetic field. The magnetic field, however, is expressed in terms of what's called the magnetic potential, and the flux which is passing through this tube does in fact influence the phase of the wave function associated to this particle. Whether it goes to the left of the solenoid or to the right of the solenoid, is a quantum mechanical experiment determines which phase that the particle has. And this measurement of the phase is sensitive enough that the single valuedness of the wave function means that the flux through this tube is quantized in units of the electric charge. So the quantization of this flux is a consequence of topology. Similarly, famous condensed matter systems people have studied extensively, the quantum Hall effect, which describe, in fact, how to measure things like resistance. This is sensitive to only edge effects of some substance. And because these are edge effects, they're topological in nature. And we can characterize the physics of these very complicated systems using very simple topological rules. So there's a universality to the behavior of these materials, and this universality arises from the role of topology in addressing how the physics is thought about. So there's a natural home for topology in physics. We already see this in the undergraduate level, and we'd like to see more aspects of topology and see what we can say about topology using modern tools. So let me proceed and tell you about knots. So knots can be thought of as a circle embedded in a three-sphere. So the simplest knot is the unknot. There's no twisting. It's just a circle that's naturally embedded in the three-sphere. And then when we add these twists, we have more complicated knots. So these are the first few knots we encounter: the trefoil, the figure eight, the cinquefoil, and the three twist knots. And they're characterized by the number of crossings. So the trefoil is the simplest non-trivial knot. There's a left-hand trefoil and a right-hand trefoil. They're mirror images of each other, but the trefoil has three crossings. The figure eight knot has four crossings, and these other knots, single foil and three twist, have five crossings. So the mathematicians organize knots in tables by crossing number. So these are the knots up to seven crossings. And crossing number is a proxy for the complexity of the knot, as we'll see. And then these are the knots up to eight crossings. There are now 21 of these knots with eight crossings. There are 49 knots with nine crossings. The list keeps going on and on. So by crossing number, I mean minimal crossing number. So even the unknot, for example, you can make look more complicated than it really is. For example, if you do these trivial sorts of twists, which you can sort of unwrap very easily just by pulling on the edges a little bit, you can see that these knots untwist very easily to the unknot. So by crossing number, we really mean minimal crossing number. Okay, so there are certain other moves besides a twist you can do to complicate and uncomplicate knots. If there are two strands that pass on top of each other, you can poke them apart. And then there is this slide, which involves three strands. And these are called Reidemeister moves. So these Reidemeister moves are knot operations that may make the knot diagram, the picture of the knot that we're seeing, the projection of the knot to two dimensions, look more complicated than it is. But these are things you can undo and make the knot simpler. So these are called Reidemeister moves, and there are three different kinds of these Reidemeister moves that you can apply to make knots simple or complicated. And if you apply these Reidemeister moves, it becomes very difficult to start distinguishing even the unknot. So these are both examples of the unknot, but even if you stare at this for a very long time, it's very difficult for you to see that these are in fact the unknot. So the tools you need to develop to discriminate between what is a knot, which knot you're talking about, can be more complicated than just looking at it. So, in fact, this is an issue that sort of propagated in literature. So, in the late 19th century, people thought about knots and were studying knots from a physical perspective already because they thought that knots represented the periodic table of the elements. So, there was this vortex theory that was developed as a precursor to atomic theory. And these vortices were, in fact, these knots. And this is why people were studying knots back in the day. And in one of the first lists of knots, at 10 crossings, there were these two knots, 10-161 and 10-162. They're examples of knots with 10 crossings, and they seem to have very, very similar properties. In fact, there's really no way to distinguish these knots, even though they look very different. But it turned out that there were Reidemeister moves. You apply in the right order, you convert one picture to the other picture. And in fact, these are the same knot. So this was only realized in 1973 by a lawyer named Perko, who was an amateur mathematician. So these errors that appear in literature are very difficult to correct just by inspection, by applying Reidemeister moves even. So we want to come up with better ways to distinguish knots, and topological invariants do the trick. So like the Euler characteristic we saw earlier, we can describe other topological invariants. They're the same, irrespective of how you draw the knot. And one such topological invariant is a polynomial invariant. It's a polynomial you write down based on the picture of the knot, and it goes by the name Jones polynomial. These are normalized so that the unknot has a Jones polynomial of 1, and all the other knots have a Jones polynomial that are relative to the description of the unknot having this Jones polynomial of 1. And you can calculate this using what are called Skene relations, which introduce certain factors of certain powers of Q based on taking a picture of a knot. So Jones realized this initially in terms of what are called von Neumann algebras. So there is an algebraic description of these objects, but you can get this polynomial by examining the knot diagram that we associate to the knot, and you get the same polynomial irrespective of how you draw the knot. So this is what makes it a topological invariant. So a question then is, can we calculate this more efficiently? It turns out one efficient way to calculate this is to use physics. So if you certain quantum field theories, these knots are natural objects in these quantum field theories. These polynomials that are not invariants arise by studying things that physicists can calculate in these quantum field theories. So in particular, the Jones polynomial is computed in a quantum field theory called Chern-Simons theory. Chern-Simons theory is a topological quantum field theory that lives in 3 dimensions, and it has a claim to being the simplest quantum field theory of them all. So in this theory, there's certain operators. These operators are associated with what are called Wilson loops. You take some curve on a 3-dimensional geometry, and along this curve, you integrate some field. This field is called the holonomy. And once we compute this holonomy of this field by taking a path-ordered exponential of the field along this loop we drew in the space, we get what's called the Wilson loop operator. This operator is evaluated in some representation of the group that's associated to this field. And the details maybe are not so important, but the idea is that by calculating certain vacuum excitation values in this quantum field theory, we're able to calculate the Jones polynomial by considering the loop to be the knot as realized in this S3. S3 is a 3-dimensional sphere, so it's a 3-dimensional space on which we can put Chern-Simons theory. The fact there's a topological invariant means that if you change the metric on the sphere, you get the same answer. So it's not related to geometric properties, it's simply related to the topological properties. This quantum field theory has an action, and this is how we're computing these vacuum excitation values using standard methods in quantum field theory given this action. Now, the point that I like to highlight is this coefficient in front of this action. This coefficient is quantized in integer units, and the integer quantization is related to, if you like, the consistency of the wave functions, the path integral associated to these quantum fields. So if you do a gauge transformation of this field A, the action needs to be invariant. The invariance of the action of the gauge transformation, which is a redundant description of the system, is given for us by the quantization of this coefficient that appears in front of the action. Okay, so in gauge theory, we can look at different groups, and the group in description of the Chern-Simons theory I'm thinking about is SU2. It's really the simplest of the Chern-Simons theories we're going to write down. And we can think about these groups as having an algebra. This algebra can be realized in terms of matrices. The different kinds of matrices that realize this algebra give what are called representations. So the group algebra of SU2 can be described by 2x2 matrices and 3x3 matrices and 4x4 matrices and so on for any integer n. And these are the n-dimensional representations. They're described by what are called Young diagrams, and the number of boxes in the Young diagram tells us which representation we're talking about. So the algebra of SU2, for example, is realized as spin in quantum mechanics, and the spin 1/2 Pauli matrices are the 2x2 representation, so-called fundamental or defining representation of SU2, and the 3x3 matrices, which also realize the same algebra, these are associated to spin 1. So if you're studying electrons, you're looking at spin 1/2. If you're studying photons, you're looking at spin 1. And similarly, the higher spins correspond to more complicated particle interactions we encounter in quantum mechanics. So the fact that in defining the Wilson loop operator in Chern-Simons theory, you have to choose a representation of SU2, that choice representation corresponds to what's called color. The colored Jones polynomial corresponds to traces in different representations. The simplest Jones polynomial is the fundamental representation Jones polynomial. That's the one that Jones defined in terms of the von Neumann algebras and can be computed combinatorially using the knot diagram. Okay, so the Jones polynomial is an invariant. I've written down the Jones polynomial for the figure 8 knot, and it's a polynomial with degrees that run from -2 to 2. And Q, the variable appearing in this polynomial, is defined in terms of K that coefficient we saw, which was an integer. It's shifted by 2 because 2 is the dual Coxeter number of the group SU2. Now, one of the open questions in knot theory is the unknot the unique knot that has a Jones polynomial equal to 1? And we don't even know if this problem is NP hard or polynomial hard. There's been a lot of work in literature on this. And in fact, studying this problem involves many famous names like Den and Turing and Haken, and more recently, Lackenby has been the one who's been making progress on the complexity class of this problem. Okay, another knot invariant is the hyperbolic volume. So if you think about a certain class of knots that are called hyperbolic knots are knots such that if you take a epsilon neighborhood around the knot and remove it from S3, the volume of the complement of the knot, what remains after you remove this epsilon neighborhood around the knot, is another knot invariant. This volume is computed in a certain metric. This metric is a hyperbolic metric, so it's a metric with constant negative curvature on the complement. So Mostow showed that this would be a unique metric, and Thurston gave us the tools for how to compute this, and this describes another knot invariant. So if your knot happens to be hyperbolic, has this property that when you remove the knot from the ambient sphere, the remaining space is one that has a constant negative curvature. The volume in that metric, which describes that constant negative curvature, is a knot invariant. And it's computed from an ideal tetrahedral decomposition of the knot complement. Okay, so if you look at the knots up to 16 crossings, it turns out that all but 32 of these are hyperbolic. So essentially every knot you encounter at low crossing number is hyperbolic. And Adams conjectured the proportion of hyperbolic knots approaches 1 as the crossing number goes to infinity. Now, it was realized that this conjecture is wrong. So this contradicts another conjecture, which tells us about the crossing number of composite knots being not less than each of its factors. Malyutin made this observation in 2016, and since then there's been a theorem that says that as you go to crossing number goes to infinity, there's some fraction of knots that are so-called satellite knots that that fraction doesn't go to 0. So the data sets we're studying are explicit data sets of knots, and we should be cautious about the conclusions we draw because the properties of data sets at small crossing number may not extend to the data sets which we're considering. We would try to assess the features of all knots. So knots that are in boxes are examples of hyperbolic knots at low crossing number. So the figure 8 is the first non-trivial example of a hyperbolic knot. Okay, so now that I've introduced these actors, let me tell you about how some of these actors are related. So there's a volume conjecture due to Kashayev, Murakami, and Gukov, which says if you take the colored Jones polynomial, these Jones polynomials are considered these various different representations of SU2, you take the limit where the dimensional representation goes to infinity, and you evaluate the Jones polynomial at a primitive root of unity, then the conjecture is that this gives you the volume of a knot complement for these hyperbolic knots. So in fact, in addition to taking the representation n goes to infinity, you also need to take the color, the coefficient k, the Chern-Simons level that appears in the action, that has to go to infinity as well, and these go to infinity in the same ratio. So if you try to evaluate this conjecture, it's difficult because in most cases we don't know how to calculate the colored Jones polynomial up to arbitrary colors. One of the knots for which we can do this is called K0. It's one of these simple knots. It's simple in the sense that even though it has 18 crossings, its volume is described by a small number of these ideal tetrahedra. I think it's 4 ideal tetrahedra to compute the volume of this particular knot. And we can therefore, because this knot is simple in this sense, calculate lots of these Jones polynomials analytically, then evaluate this conjecture by plugging in these different phases for these different polynomials. And we find that indeed, as you go to large n, large representation, large color, the evaluation of the Jones polynomial does in fact recover the volume. However, the convergence is not that fast, And moreover, the behavior is not monotonic in that you get worse before you get better. So we would like maybe to come up with a better version of the volume conjecture that has nicer properties than this one that's been initially formulated. Okay, so in writing a Jones polynomial, the example I gave you, for example, for the figure 8, had integer coefficients. As far as the physics is concerned, there's no reason for these to be integer, although, from the combinatorial perspective, it seems to make sense that because you're looking at certain crossings in these things, you get integers from that perspective. So the physics story is less clear on this point, and an explanation for why these coefficients of integers is given by something called Kavanagh homology, which is a categorification of the Jones polynomial. And this was explained in the early 2000s by Kavanagh and Barnaton and others. So one thing that was observed is even if you look at the ordinary Jones polynomial and you evaluate it at -1, which is the root of unity suggested by the volume conjecture, you find there's some vaguely linear relationship between this evaluation and the volume. Similarly, certain quantities computed in Kavanagh homology also have this relationship to the volume. So I've introduced a bunch of characters, and there's this famous absurdist play by Luigi Pirandello called Six Characters in Search of an Author. And the author I'll propose that relates some of these things together in the story is a neural network. So feed-forward neural networks have a very long history. They date back to Rosenblatt in 1957. He was a researcher at the Cornell Aeronautics Laboratory, the Naval Research Lab in the United States, and he developed what's called a perceptron model. In the perceptron model, you think about an input vector, and the components of this input vector are all weighted differently. And by weighting these components and then maybe shifting them slightly, and then evaluating them using a very simple function, sigma, called an activation function, which is in particular nonlinear, you can find an approximation to an output to generate from the components of the input vector. So the different nonlinearities one can apply are often the sigmoid or the ReLU function or the tanh. These are elementary functions we're using in order to evaluate and express this nonlinearity. So if you instead of having just one perceptron or one neuron, if you have a bunch of these in different layers, you build what's called a feed-forward neural network, and essentially you think about a weight matrix as moving you from one vector to another vector, which you can shift with what's called a bias vector. And then once you have this new vector after these linear transformations, these affine transformations you're making, then you evaluate each of these components with this nonlinearity you specified. The goal is to match the output, for example, the sum of the components of the final vector you get with a desired input. So this is the philosophy of supervised machine learning. And you use these iterated layers with these different nonlinearities. You compare your prediction to the ground truth, the answer that you know, and then you tune some weight function, some loss function that you minimize during training, such that the parameters of the weight matrices and the bias vectors are chosen in order to make the predicted value of your neural network resemble the actual value you're using in training for the answers that you know. And this idea of using feed-forward neural networks in order to make these predictions won last year's the 2024 Nobel Prize in Physics, hinted in Hopfield 1 for these kinds of tools. Okay, so in our case, we have some neural network that can predict the volume from the Jones polynomial. We think of the Jones polynomial as being characterized by its minimum and maximum degrees and by the coefficients that appear in front of each of the terms in this polynomial. This is some vector we feed into some neural network. And then we predict the volume of the knot complement for these hyperbolic knots, which are essentially all knots up to the 16 crossings we've been studying. So up to 16 crossings, the Jones polynomial is represented as 18 vectors. It's just the minimum degree, the maximum degree, the coefficients, as I mentioned, and a very simple two-layer neural network with 120,000, sorry, with 12,000 parameters to tune these weight matrix elements, these bias vector elements. This can make a prediction with high accuracy. So here's a picture of the prediction. So based on the training, with 10% of 313,000 knots up to 15 crossings, we make a prediction of the volume and we get a 2% error. So this is work that I did with Arjun Kar and Ankar Parikar back in 2019. So this is one of my first experiments with machine learning and mathematics. So the code, which makes this prediction, is just 2 lines of Mathematica. So this is what made it particularly easy for us to get into this field because the things are often built-in functions in software we use regularly, and it's very easy to apply these methods to data sets that we have. So this is some real-time execution of this code. The orange function, which is getting smaller and smaller, is this loss function, which describes the difference between the prediction and the actual value that are used in training. So I'm using 10% of knots up to 15 crossings for this training set. And I'm generating basically the picture you saw previously that I showed you. So this is the training process. This is real-time running. So it takes a few seconds. This is in fact a video I made several years ago, so it runs much, much faster on a modern laptop, and we get this picture that I plotted earlier. So this is very easy to use and very quick, and it lets you make certain connections that you may not have made previously. So it's a little more complicated than this, but to be very, very simplified. A neural network is very good at finding correlations in columns in a spreadsheet. If you can organize your data so that you have columns in a spreadsheet, for example, one polynomial invariant and other polynomial invariant and so on, you can find relations between polynomial invariants and these other topological invariants that you've organized for these knots. So a result is that the volume is a function of the Jones polynomial, and there may be some small corrections. The small corrections, because the Jones polynomial does not uniquely identify a knot, you have different knots that have the same Jones polynomial with different volumes for their knot complements. When this happens, the average spread in the volume is about 2.5%, and the neural network has that same error. So it does roughly as well as can be expected on this data set. The same applies to data sets that are larger. So we use the 1.7 million hyperbolic knots up to 16 crossings. There are about 841,000 unique polynomials, and we see that there are similar errors. These databases can all be compiled from existing software and data sets that are on the web. Now, there are very few exact results in machine learning. One of these is the universal approximation theorem, which says that a neural network with a sigmoid activation function and a single hidden layer with a finite number of neurons can approximate any continuous function that's suitably well behaved on compact subsets of Rn. They're not very good at extrapolating beyond the compact subset that's used for training, but it can make this approximation to arbitrary accuracy. Surprise here is the architecture we use to do this job is extremely simple. And this suggests maybe there's an underlying reason why this calculation that relates the volume to the knot complement is a simple one. Remember, the volume conjecture requires us to take this n goes to infinity limit, whereas the data we're feeding it are at n equals 2. They're the ordinary Jones polynomial, and 2 is rather far from infinity. So we want to see why the ordinary Jones polynomial knows so much about the volume. And in the process, we seek to reverse engineer this neural network and maybe get some intuition for why this is working so well from quantum field theory, from physics. So when we were studying this during the COVID years, my student at the time, Jessica Craven, made this observation that there's this tool in the computer science literature called layer-wise relevance propagation that may be useful to us. What this tool does is it assigns a relevance score to each neuron in your neural network and also to each input feature in the 0th layer of your neural network. And the relevant score is computed just by taking the activation functions we had, the weights and the biases. The scores are normalized so that at each layer, the scores add up to 1. So you want to see which input feature is most responsible for the prediction by assigning these relevant scores to each of the vectors that appear in the input. So we looked at different kinds of inputs, and one kind of input we looked at was evaluations of the Jones polynomial at different phases. And by studying this, I'm not going to go through details here, but we have these relevant scores represented by these colors, and the red colors are the ones that are most relevant, and the different knots are the different columns in this diagram. And we see for these different knots, the same rows are red. So this suggests that certain phases, evaluations of the Jones polynomial at certain phases, are responsible for making a prediction of the volume to this very high accuracy. So if we evaluate at a bunch of these different phases, we find that a phase that's near 3 pi over 4 is the one that works the best. And we see that different values of the phase have different mean absolute error in using this neural network. So there's some features of this graph. So the worst error you get is like 12%. That's just doing the stupidest thing possible, assigning the average volume to every knot that you encounter. And when you do that, you get a 12% error. So it describes a latent error in the data set. But if you choose other phases, you find that the error improved significantly down to about that 2% we were seeing. Now, we also noticed that for certain values of the phases, we can translate these phases to the Chern-Simons level. And the Chern-Simons level is the coefficient which appeared in front of the action, you remember. And we remember the definition of Q is e to the 2 pi I over k plus 2. So we can translate the phase we're looking at back to a Chern-Simons level. The integer Chern-Simons levels, 1, 2, 3, etc., these all have the same 12% error. So in fact, k equals 1, the graph sort of is got a spike there. So the error goes bad at the integer levels. But the non-integer levels, they're the ones that give us some data about the volume. So the best phase, either the 3 pi I over 4 times I, that phase corresponds to Chern-Simons level k equals 2/3. And as I said, the consistency of the quantum field theory, the consistency under gauge transformation, require this number to be an integer. So somehow, if it's not an integer, that's when this method works. So what's going on here? This behavior is explainable by an analytic continuation of Chern-Simons theory that Witten presented, and we, in our paper, explain what's going on in detail. And the features that we saw in the previous graph are a consequence of certain integration cycles in this analytically continued Chern-Simons theory. So basically, the approximation formula that we've developed that does nearly as well as a neural network. So I've written down a simple function here that has roughly the same error as a neural network's error, 2.8%. This function that I've written down above the plot is one that we essentially got from taking this evaluation of the Jones polynomial and then regressing with a small number of coefficients to determine. Three different numbers give us this plot. So roughly speaking, this approximation formula works well for levels k for which a certain geometric conjugate connection makes a contribution to the Chern-Simons path integral. So this is a flat connection that is a saddle point of the action. And the integer levels have a term which looks like 1 minus e to the 2 pi I k, where k is now an integer. Because e to the 2 pi I k for integers is equal to 1, that washes away any information about this geometric conjugate connection. But for non-integer values, this flat connection does play a role. And because this flat connection has information about the volume built into it, then we're able to make this prediction as a consequence of this analytic continuation of this Chern-Simons theory. So it's a nice explanation in terms of physics for the features we're seeing that sort of explains why this learning is happening. We can do the same by compiling a data set of adjoint polynomials. These are polynomials corresponding to 3 by 3 matrices that represent the SU2 algebra. And we find there's a different phase that works here. And the best phase here is not the same value we saw previously. The best phase here is 8 pi I over 15. And given 2 data points, we sort of extrapolate and we find some conjecture for a phase which works for arbitrary matrices for these higher colored polynomials. And we're trying to calculate data sets that enable us to make this comparison and see whether these predictions are correct. So this is some recent work I've done earlier this year with Mark Hughes and Ramadevi and Pratik Roy, who was my postdoc at WITS, and Vivek Singh, who's a postdoc at NYU. Okay, so we can evaluate this best phase conjecture for certain knots for which we can compute Lofton Lossa-Jones polynomials, figure 8 being one of them, and we find that our conjectured phase works better in the phase that the volume conjecture is proposing. And the same applies as knot K0, but again, things are still non-monotonic, so hopefully we can do better and refine a more nicer version of the volume conjecture eventually by playing with data. Knot theory, because of the existence of all these vast catalogs of topological invariants, is a playground other people have looked at. The DeepMind group, for example, played certain games. Instead of using layer-wise relevance propagation, they use what's called saliency analysis. But the idea is the same. They feed in a bunch of features, and they predict some output, and they see which features are the most important. The most salient features are the ones with the highest gradients when you backpropagate, and you make some small shifts in data. They were able, based on these experiments, to propose a conjecture that relates a bunch of different knot invariants together, and they were then able to prove this conjecture using the usual tools of mathematics. So this is a theorem which was inspired by machine learning, and there have been other results in this direction as well. I list a few of these papers. I've got some other papers that relate knot invariants to each other. So this is a useful playground to explore. One of the reasons this is of interest is there's a famous conjecture in mathematics called the Poincare conjecture, which says that anything which looks like a sphere is a sphere. And it's mostly resolved in various dimensions. And in fact, the resolutions in various dimensions typically win people Fields medals. The full answer in 4 dimensions is not known, but it's related to knot theory, and the existence of these exotic spheres in 4 dimensions is unknown. But the relation to knot theory comes because of thinking about the spheres as boundaries of certain balls in which you can embed Riemann surfaces whose boundaries are the knots themselves. And if these certain knots have certain properties, these provide counterexamples of the Poincare conjecture. So we're studying whether learning certain topological invariants of a size genus using machine learning methods can enable us to find attractive counterexamples, candidate counterexamples to study more seriously using traditional methods. So this is an area that we're exploring in seeing how machine learning is useful for addressing a very important open problem in mathematics. Okay, so this finishes my discussion of my first case study. Second case study, Clavier manifolds, and then I'll conclude with some words about where this all is heading, but I'll pause for questions if there are any. Good. Let me talk about Clavier manifolds then. So I'm a physicist. One of the things I study as a string theorist is how gravity and particle physics talk to each other. And our theory of gravity in 4 dimensions is the theory that Einstein developed, it's general relativity, and it has the feature that it relates geometry of space-time to the presence of energy or matter in the space-time. And really the geometry's response to the presence of energy, and conversely, the curvature of space-time tells matter how to move in this geometry. So this is one of these very well-tested theories we're very, very confident about. It applies from microscopic scales all the way to cosmic scales. Another theory which you're very happy about is the standard model of particle physics. It tells us how the particles are organized. It tells us about electromagnetism, the weak force, which explains radioactive decay, strong force, which explains how protons and neutrons are put together, the Higgs effect, which gives particles their mass. All of these described by the standard model. The standard model is the best tested theory in the history of science. If you make a measurement of quantity and you compute the theoretical value of the quantity, these things agree to 13 decimal places. There's nothing else like it anywhere in science. So this is the best tested theory we have. And it's a quantum field theory. It's one of these theories that physicists like to think about. Now, one of the features that we liked about general relativity was that it was geometric. The difficulty is there's a theorem, the Coulomb-Mandula theorem, which says that non-gravitational interactions are not encoded as geometry. So we can't really think about the standard model in the same geometric way as we think about the uh, uh, the physics of gravity. But there's a loophole. The loophole is we think about higher dimensional geometry. And the internal symmetries associated to gauge theories, like the standard model, can arise from looking at the geometry of these higher dimensions. And the simplest example is due to Kaluza and Klein, who took the five-dimensional Einstein equations in the space that's flat with a circle attached to it. And in the limit where the circle becomes small, they're able to recover four-dimensional Einstein equations in the presence of electromagnetic fields. So they get Einstein gravity plus the Maxwell equations. And the fact that the symmetry group of the circle, S1, is U1, and electromagnetism is a U1 gauge theory, is not an accident. So the realization of electromagnetism comes from the geometry in the higher dimensions, the symmetries associated to that higher dimensional geometry. This is a notion of compactification, and string theory has developed this by thinking about a 10-dimensional theory that goes down to 4 dimensions. The 10-dimensional theory is where the gravity is consistent in its interactions with quantum field theory. And one such example of this geometry is illustrated in this spinning little picture. These are different slices, what's called a Calabi-Yau manifold. And a Calabi-Yau manifold is a complex Kähler manifold that emits a Ricci flat metric. And in a different vein, I've been looking at finding numerical approximations of this Ricci flat metric using neural networks, since analytic expressions are not known. But we want to think about how to get particle physics from string theory. So we think about compactifying string theory, not on a circle anymore, a la Kaluza and Klein, but on one of these Calabi-Yau spaces. These Calabi-Yau spaces are nice because they're this Ricci flat metric, which Yau's theorem famously establishes in these manifolds, enables the space to solve the classical Einstein equations. So it's a background for string theory. And when you think about the space as being very, very small, the effective field theory you get in 4 dimensions is no longer just electromagnetism, but is a nice field theory. It turns out to have what's called n=1 supersymmetry. And there's some nice mathematical structure associated to n=1 supersymmetry. And natural extensions of the standard model enjoy this extra supersymmetry. The supersymmetry is a symmetry which relates what are called fermions to bosons. There's a one-to-one correspondence to each other. Fermions are particles with half integer spin. Bosons are particles with integer spin. So there's some nice particle physics description of what's going on as well. So to get an unreal world with supersymmetry, since in the real world we don't see a particle with the same mass as the electron that's bosonic in character, we want to think about these as toy models for nature. And these toy models come from compactifying string theory on these Calabi-Yaus. The simplest example of a Calabi-Yau is a complex manifold. So it's the simplest example has got 2 real dimensions. It's just a torus. And the torus is characterized by 2 parameters, one which tells us about the size, the volume, the other which tells us about the shape. So you can think about a torus as being projected onto some fundamental region of the complex plane. And you can think about an old school video game with periodic boundary conditions. So if you disappear on the left, you appear on the right. If you disappear on the top, you appear on the bottom. These describe what are called cycles on the torus. And the shape of this fundamental region is this shape parameter, this complex structure parameter that I associate to the torus. And the area of this fundamental region is the size parameter that associates to the torus. In math parlance, they're called Kähler parameters and complex structure parameters. So Calabi-Yau's are often of toric type, meaning that we realize as toric hypersurfaces. And the list of which Calabi-Yaus exist in various dimensions are obtained from reflexive polytopes, which are certain polyhedra, lattice polyhedra with some properties that I'll explain briefly. And this connection between these Calabi-Yau manifolds and these lattice polytopes was developed by Batarev and Borisov. And it turns out that there are 4,319 three-dimensional polytopes associated to the Calabi-Yau K3. This is the Calabi-Yau with two complex dimensions. And there are 500,000 four-dimensional polytopes to give us Calabi-Yau threefolds. And these are, we don't know how many Calabi-Yau threefolds there are, and we don't even know how many polytopes there are for fourfolds. But using machine learning, you can also discover new relationships between features of these polytopes. And we found a new formula, for example, for the Euler characteristic for the threefolds by just playing with neural networks. We, as I said, don't know a complete list of polytopes in 5 dimensions. Kreutzer and Skarka gave us a list in 4 dimensions. It's comprehensive, but something similar doesn't exist in higher dimensions, largely because there are too many of these. And we'll use machine learning techniques in order to find new polytopes from which we can build new Calabi-Yaus. So I mentioned these reflexive polytopes. Reflexive polytope is a polytope with lattice vertices and a single interior point, which we can take to be the origin. So in 2 dimensions, I give you 2 examples of such polytopes. There's the origin, and there's a triangle, and there's a square, and the vertices are all lattice points, and the edges are a unit distance away from the origin. So such polytopes are called reflexive when they only have a single interior point. The complete list is 16 of these in 2 dimensions. And we don't know, as I said, how many there are in higher dimensions. An estimate may be 10 to the 18 in 5D. So you'll never have a complete list of these. It's just too much data to even store. So we used machine learning, so-called genetic algorithms, in order to construct these polytopes in higher dimensions. The idea is that you look at some fitness score, which tells you how close you are to being reflexive. You rank your polytopes by this fitness score, and then you apply the ideas of Darwin by thinking about mutating and breeding members of this population. And you get some new population, and you evaluate the fitness score of these and see how close they are to being reflexive. And you keep going this way. And after a number of cycles of this algorithm, you end up finding a population that has the features that you desire. So this is a nice way of scanning through high-dimensional data sets or high-dimensional spaces in search of particular points of interest. So we can construct some fitness function that tells you how close you are to being reflexive and apply this fitness function. And in this way, find new 5-dimensional reflexive polytopes that give us new Calabi-Yau fourfolds that inherit Hodge numbers from these polytopes. And these are new geometries for string compactification. And this is another application of machine learning to topology, because we're finding geometries with new topological properties using these tools. So this is an area that I've been thinking about. And now we're thinking about what we can do with these new manifolds we construct. And for example, certain nice supersymmetry properties arise when these topological invariants have certain values. We can find geometries that have those values. So we're finding interesting geometries for string theory from these explorations. Okay, so I'm almost out of time. Let me conclude with some prospects for what's coming. So if you recall, when computers started being used in mathematics in a serious sort of way was in the 1950s and 1960s, when the construction of the finite simple groups, especially the exceptional groups, the sporadic groups in this list, in order to calculate character tables for these groups, we sometimes needed to use computers. And this was sort of the first use case of computers in mathematics in a serious way that required the use of computers in order to make progress on various problems. Famously, the proof of the four-color theorem by Oppel and Hawken was a proof by exhaustion, and this proof also relied on drawing all the possible ways to uh, um, to have borders on a graph and show that all these borders can be covered using four colors. This is also done using computers. This was in the 1970s. So we had examples from the 60s and 70s of computers being crucial to certain developments in mathematics. So far, there hasn't been a use case of the same importance in applying machine learning. So we're looking for an example of a use case in which a really important result is reliant upon machine learning in a very crucial way. And the investigations of smooth Poincare conjecture in four dimensions is maybe one area in which these tools can have some impact. So we're also trying to come up with new ways of doing mathematics. So we know that neural networks, for example, are a way that we can approximate functions to arbitrary accuracy. There's in some sense a black box that knows semantics without knowing any syntax in terms of languages. Computers are becoming creative in that there are new opening sequences in Go that are devised by AlphaZero. And then there are these new developments that are happening. There are proofs in real analysis that computers write, which mathematicians can't distinguish from graduate student written proofs. There are these new proof assistants like Lean that are formalizing mathematics to prevent mathematicians from making mistakes. There are now large language models that communicate to these programs like Lean. And now with logical reasoning and natural language and all of these things being fused together, maybe it's time to learn how to collaborate effectively with Silicon colleagues. And it's not inconceivable that within 10 or 20 years, the best mathematician, the best physicist in the world will not be human. So we may be reliant upon these technologies in order to make progress in our various fields. So I think it's time now to think seriously about how to use these tools most effectively in order to discover new mathematics and new physics. So with that, thank you.
How long did it take for you to train the neural network?
I showed you the real-time training in one of these plots. So it was less than 30 seconds.
Oh, okay. And then are there any other machine learning models you considered besides the neural network?
Well, I mean, for the knot theory problems, I've mostly been using neural networks. I've also been using reinforcement learning for some other problems. I've been using transformers as well. For the Clavier problems, I've mostly been using reinforcement learning and genetic algorithms.
It's very interesting how machine learning is now being integrated into different fields now. So
Yeah.
It's very interested to see how it integrated with your field of study. Excited to see
Yeah,
that as well. And also the future plans that you have. Kind of, yeah. So thank you very much for the talk. There's no other questions. So yeah, I think we'll say goodbye. And
all right, thank you.
yeah, thanks very much.